Alrighty, Mr. Armke back with you for Sec 110. Today we're getting into Chapter 7, which is administering a secure network. So our objectives are fourfold. We're going to talk about some functions of secure network protocols, placement of security devices and technologies, how security data can be analyzed, and how to manage and secure network platforms. And we're even going to talk a little bit about as a service platforms as well. So first things first, we have to establish, as we do in any networking class, what a protocol is. Protocols are just rules for communication, and they are absolutely essential for proper communication between devices, be they network, storage, anything. If a device can't interpret the commands coming to it from the OS and can't produce an output that's usable by that OS, then it's not of benefit to the system. TCP/IP, or Transmission Control / Internet Protocol, is the most common suite that's used for local area networks and the Internet. Now, when we say suite, when it comes to protocols, what we're talking about is a series of protocols being used for common purpose. There's several protocols that function together. IP, or Internet Protocol, functions primarily at OSI layer 3, as you might imagine, the network layer, and is going to provide network addressing and routing. TCP functions at layer 4, transport protocol there, establishes connections and deals with reliable data transport. So that's the authentication handshake, making sure things arrive in the correct order, being able to resubmit pieces of a fragmented transmission that did not arrive correctly. TCP/IP itself uses a 4-layer architecture that is a simplification, if you will, of the OSI model. So if we look here at figure 7.1 in the graphic, you can see that we merge layers 5, 6, and 7, as well as layers 1 and 2. Pretty minimal there. We're just going to turn physical and data link into network interface. So going between the cabling at one end into the encoding and stuff that we need at the data link layer, we're going to just lump all that together. And then for the application layer, that comprises application presentation and session, which deals with app side controls, formatting, and maintaining the connectivity and all of the different aspects of the conversation and session between both the recipient host and the sending host. The only thing that really changes on layer 3 is the name, because we're not using any of the other various network protocols that might be there. We're focusing specifically on internet. So some other TCP/IP protocols we might deal with relate to security. So SNMP, Simple Network Management Protocol, DNS, Domain Name Service, and FTP, File Transfer Protocol. There's also email protocols that we have to be aware of that are not natively secure. They do not have intrinsic encryption. So this means that even though they are not necessarily natively going to be able to give us a secure solution, it doesn't mean that we can't use them. It just means that we'll have a little bit of extra work to do. So for something like Telnet, for instance, we could have an application-based encryption that is going to prevent some of the potential vulnerabilities that exist in transmitting things in clear text. SNMP is used to manage quite a bit of our network equipment and is supported by most equipment manufacturers. The thing about protocols that are successful is that they tend to have a large consensus. There's a lot of people that use them. They're usually open source so that they can be easily modified and observed. SNMP allows admins to remotely monitor, manage, and configure network devices. How do we do this? Well, we exchange management information between those devices, and each SNMP managed device will then have an agent or service that listens for and executes commands. The agents are password protected, and this password is known as a community string. Now, in versions 1 and 2 of SNMP, there were some vulnerabilities that were present because there wasn't individual authentication. It was a device-based thing. Version 3, now they have usernames and passwords in addition to the encryption. DNS, Domain Name System, is a protocol we use to map IPs to their symbolic names, often their FQDN, or fully qualified domain names. These hierarchical databases, which there are several, it's a distributed network, consists of site names and corresponding IPs. And the part that people miss when we talk about distribution is not a lack of efficacy. On the other hand, conversely, it is going to prevent bottlenecking to where one single DNS server or one of very few doesn't start getting bogged down by a large number of requests. Distributed DNS servers tend to be very useful. It ensures a lot of efficiency. I would rather have a DNS server that's sitting idle part of the time than one that's sitting there and just struggling to put out any other type of request. Because it is so useful and it is so commonly used for everything, because goodness knows if we had to remember Google based on their IP address rather than using a more semantically friendly domain name, we'd be up a creek, right? DNS is often the focus of attacks. Anything useful, especially something that's so pivotal, will be subject of attacks. DNS poisoning substitutes fraudulent IPs and can be performed via either a local host table or an external server. So poisoning DNS can occur either at the host level, with an individual's computer, or something that's a bit more widespread. This tends to be thwarted by what we call DNS SEC or DNS sec, the security extension set for DNS. This allows additional records and header info to be integrated into the DNS records in order to verify data integrity and make sure that the communication between two individuals, be it the server and the host, is able to be verified much more easily. Another potential issue is a zone transfer attack. This is where an attacker is going to ask a valid DNS server for a zone transfer. These transitions are actually going to allow that attacker to gain access, in some cases, to network information, hardware information, and the operating system of the DNS server and of certain devices that are connected to it. So it's able to move from one DNS zone to another. This is supposed to be a fail-safe in order to prevent a DNS server that is malfunctioning from basically bogging the whole system. It allows you to pass your request on. FTP, File Transfer Protocol, used for transferring files. It's right there in the name, thankfully. It is a non-secure protocol, so just like I said with Telnet a little bit earlier, if you want to involve some form of encryption, you can, but it is something that's going to be your responsibility to get it done. It's used to connect to FTP servers, so like most protocols, there's a specific designation that goes between where you are and where someone else is, and we want to make sure that we're creating a clear tunnel between those two. FTP on a local host computer can be done through command prompt, a web browser, or through an FTP client. The one I tend to use and the one that Mr. Ciampa uses here, or Dr. Ciampa, I believe, is FileZilla. So this is one that you can use to set up directories and be able to parse everything together for updating directories both remotely and locally. FTP can sometimes present challenges, especially if we're trying to use secure things like a firewall. So the challenge here lies in the fact that FTP uses 2 ports to carry out its information transfer. Port 20 acts as the data port, that's where everything moves, and then port 21 is our control port. Now in active mode, FTP may actually cause the client firewall to drop packets on port 20. If it's in passive mode, where the client sends the PASV command to port 21, the server will then return the port to launch a data channel, basically identifying which channel it should use to be able to pass things through. So that can be kind of messy. If you have something that's saying this is where the data is coming from, and then this is messages about that data, it's more easy in most cases to deal with something like HTTP, where it says, okay, we're going to have information about the payload rather than having the payload separate from the header. Another bit of vulnerability, because it doesn't use encryption, FTP is vulnerable to a man-in-the-middle attack, meaning that you can have your transmission hijacked and be receiving files that are either corrupted or invalid. So you always want to make sure that if you're using FTP for file transfer, especially for larger files or a large number of files, that you're incorporating some secure transmission options. And we have 2 fairly good ones. We've got FTPS, which is the Secure Socket Layer FTP. It incorporates SSL and TLS to encrypt commands over port 21. The data port is not going to be encrypted, but at least you know the information that's controlling that data flow is not being messed with. SFTP, on the other hand, Secure FTP, is much better. It uses a single port instead of 2, and all data and commands on it are encrypted. So when I transfer something using the FTP protocol, I tend to use the variant SFTP rather than FTPS, as much as I love SSL. Email. we talked about how email can be unsecured. So we've got a couple of different ways we can involve this. We've talked about mail gateways before, but we also want to make sure that we're paying attention to the software solutions as well. So there is a protocol called SMIME, or Secure/Multipurpose Internet Mail Extensions, that we can use to secure email messages. Now, if mail is being accessed via the web with IMAP instead of a dedicated application, SMIME will fail. So we want to make sure that if we're using something like an IMAP connection via a web browser, if you're going through Google for your mail, I would recommend that you use an HTTPS connection where possible. And then, of course, there are other encryption packs that can be involved for IMAP. Now, because SMIME encrypts the entire message, this complicates malware inspection tools. So if something is viewing your email, or at least trying to get a look at the header to make sure something isn't potentially going to damage your system, it would also be encrypted. So you can only run the scan after the email message has downloaded and decrypted rather, which could be too late. Some enterprises will automate the encryption and decryption process via mail gateway, so that can be a hardware solution for a software problem. Here we have a couple of different secure network protocols based on different types of media. So voice and video, you usually see SRTP. So instead of just regular RTP, real-time transport, you're going to see secure real-time transport here. NTP we would use for time synchronization, SMIME for email, HTTPS for web browsing. A lot of these just involve adding S. And then, of course, we get into VPNs for remote access, DNSSEC for domain name resolution, and then IPsec for routing, switching, NAT, and subscription services. The placement of devices is important. See here in figure 7.6, the structure of these things is set up very particularly because if we do not have devices properly located in the architecture, the protection they offer can be negated. Essentially, if you put a switch ahead of a firewall, that switch's traffic is going to be much more vulnerable than if you put it correctly behind the firewall. So one of the examples is an SSL/TLS accelerator. This is a device that can be attached into a web server. Usually it's a slot card, and it's going to contain dedicated coprocessors to handle your SSL and TLS processing, because SSL and TLS is slightly more computationally intensive. This module can be installed as a virtual server as well, alongside a forward proxy. Port mirroring, this is going to allow an administrator to configure a switch to copy traffic from some or all ports to a designated port on the switch, which would then pass to, in the graphic here we see a network analyzer. You may also see what's called a network TAP, or TAP, test access point. So this isn't just a standard tap like we would think of as like, a soda tap or a beer tap. This is an acronym that is not always capitalized. So if you see like ISA-TAP adapters for VPNs or for IPv6, that's what it's talking about, as a test access point in certain cases. This is a device that allows you to monitor traffic directly rather than just strictly copying it. Sensors, collectors, and filters. These should be at the data stream's largest point where most traffic is moving. Sensors are going to monitor for intrusion and prevention devices. Collectors are going to gather traffic for SIEM. And filters will block traffic for content filters. So these things should be placed in an area where they will be most effective. Aggregation switches. This is where we combine multiple connections into a single link. They should be sited between routers and servers in order to detect and stop attacks directed at a server or application. So they need to be in the junction between local and remote traffic. This is going to funnel everything down into a kind of bottleneck. But aggregation switches tend to be built well enough to where they do not negatively affect network traffic unless there's something wrong with their configuration. Again, bad configuration can lead to completely negating the benefits of the hardware in the first place. Correlation engine. This is a system that aggregates and correlates content from sources to uncover either an attack's origin or presence on the system. It should be in the internal network, the protected side, using the logs of different hardware devices in order to show potential avenues for attack. Again, we're all about minimizing the attack surface and examining where we can try and reduce potential intrusions. DDoS mitigators. These are hardware that identify and block real-time DDoS attacks, and they should be where they can monitor the largest stream of data, not too far off from where we looked at for sensors, collectors, and filters. Security logs, of course, can reveal attacks directed at the network and if they were successful. So it's important to be able to go over those and identify potential issues. Access logs, where users could be compromised or if somebody's using falsified or escalated credentials. Audit logs to figure out which user performed an action that led to a particular result. Again, auditing is a big part of GRC, which we'll talk about in a little bit, governance, risk management, and compliance. Event logs document unsuccessful events and the most significant successful events. So, just, opening a program, not a big deal, but if it's a protected program or if it's accessing a particular database, that would be significant. Unsuccessful events are, password failed to access or a particular port was rejecting traffic. Those things can help us to identify where a potential intrusion may be occurring. Routine log audits help us to identify security incidents, policy violations, fraudulent activity, and operational problems. So let's look at this. Let's unpack this for a second. Security incidents, of course, is pretty self-explanatory. We have an issue with something going on in our security platform. But where does that originate? If it's a policy problem, meaning that somebody isn't obeying the rules, then we can censure that person, or we can, have a discussion about why they were performing the action that they were. Maybe they were unaware that that was a particularly prohibited activity. Again, we can coach from there. People are either untrained or unwilling, as one of my old managers used to say. So I like to kind of stick to the idea of if you're unaware, we can fix that. If you're unwilling, then we have a problem. Disciplinary actions must be a little bit more severe at that point because we have to impress upon you the reason why this policy exists. Fraudulent activity, obviously that makes pretty clear sense. If something's trying to go on that shouldn't be going on, obviously we need to identify that. Operational problems, if we have a problem with how the rules are written, then obviously that is a systematic problem. That will happen more than once. That's why we need to audit regularly and vigorously, because we need to be able to identify, is this a problem that's going to come back and bite us again? Logs also help us to perform auditing analysis, as well as supporting internal investigations and identifying operational trends and long-term problems. So the internal investigations thing kind of ties into policy violations and fraudulent activity. The operational trends and long-term problems are problems with the platform. So logs cover a lot of ground for us, and they also provide what's called non-repudiation, which we've talked about before. Basically, it removes somebody's ability to deny that they did something because their credentials are the one attached. Now, this is not always to say that somebody didn't have their credentials compromised or whatever else, but that is still something we need to investigate. If we have, John Doe as a user and their materials are compromised, we need to figure out why. And we need to figure out whether or not there was something with volition behind it. Was it a person? Was it an error? Or was it somebody external to the system who got a hold of somebody's stuff by, cracking a password, guessing, breaking a digest, that sort of thing. Logs also provide documentation of legal and regulatory compliance requirements. So if we take credit cards, for instance, our particular company, we need to make sure that we're compliant with PCI DSS. We need to make sure that's payment card industry, data security standards. Lost it for a second. Data security standards. So if we're not compliant, obviously we could open ourselves up to legal action. So we need to make sure that's involved. If we need to be able to report things to the Department of Commerce or another financial regulatory commission, those logs will make sure that if something comes about and it looks like we're in the wrong, we have ways to prove excuse me, where we were or were not compliant, so that way, be there a need for punishment or not, it's fair. We are actually honestly observing the letter of the law. Data from devices. Almost every hardware device designed for security will generate logs. You can generate logs from all kinds of events. Firewall logs in particular, we have 5 main things we should examine. As I talked about earlier, unsuccessful events are usually pretty prominent. IP addresses that are rejected and dropped, probes to ports with no application services. That can be an example of somebody trying to do an Nmap run. Source routed packets, suspicious outbound connections, and unsuccessful logins. Now, security software can produce important data that can be analyzed. We often fall into 2 categories on that, DEP and FIC. Data execution prevention is a Windows feature that prevents attackers from using buffer overflow to execute malware. Talked about buffer overflow before, trying to trigger a negative number wraparound. DEP and similar software events can be logged along with their level of severity. So, just because DEP triggers doesn't mean it's something critical, but we can see trends. And trends are much more important than one-time incidents. File integrity check. This is going to monitor changes that have been made to computer files such as operating system or utility files. And these changes can compromise security and indicate that a breach has occurred. So we want to be aware of a particular subset of files. So we can set FIC to monitor particular directories, things like that. So here we see some different tools we can implement, like whitelisting, so that we only permit known good activity. Removable media control, so we can control how things are introduced by removable media such as USB or SD cards, especially for routers, switches, and servers that have USB ports that can accept information externally for purposes of updating an OS or updating an application. Advanced malware management is usually done as a third-party service, and this is going to monitor a network for unusual activity. Now, it does have to establish a baseline because we are using heuristics, so it's behavior based on anomaly checking and experiential data. Now, there are some issues with log management, as you might guess. Generating, transmitting, storing, analyzing, and disposing of log data means that we have to have all kinds of compliance and privacy data in place for that. And this is because there's a ton of devices that are generating logs, and sometimes multiple logs from different events, which produces a very large volume of data that are in a variety of formats. So how do we do this? How do we fix it? In this case, we have Manage Engine in the graphic on the right. This is a centralized device log analyzer. So this can do part of that correlation stuff we were talking about earlier, making sure we can identify trends over the entire network based on commonalities. Now, some applications and platforms require special security situations, especially things that deal with extending the very essential hardware and software of a business outside of the physical parameters of the building. When we start letting somebody else have a go at handling our materials for us, even in a secured environment, it should still make you a little bit nervous. Virtualization is an excellent example of that, cloud computing, and of course software-defined networking. So virtualization is just the process of managing and presenting logical resources without regard to physical topology. That means in layman's terms is we're going to get the hardware and software running as far as the OS can see without worrying about whether or not one particular device is in Florida and the other one's in Iowa. Over the network, it's all considered the same. There might be a little bit of latency, but in general, they're able to behave as if they were physically present near each other. Host virtualization is where an entire OS environment is simulated. A virtual machine is a simulated software-based emulation of a computer. So software emulating hardware is often the three-word definition that I use. The host will run a program that manages and supports the virtual OS and guest systems, and this is called a hypervisor. Now, the hypervisor is in charge of managing the resources and operating systems of those VMs. How it does it is kind of important because that defines the types of hypervisors we work with. Type 1 is what's called a bare metal hypervisor, and it runs directly on the computer hardware as opposed to the underlying OS. Type 2 is going to run on the host OS and have Windows or Mac or whatever else underneath it, and it's running in a container inside of that environment. A container or application cell is going to be something that holds only the necessary components for that particular application or OS to run. It reduces the amount of hard drive storage that's necessary and for the amount of RAM you need. This allows containers to start up a lot more quickly because we don't actually have to initialize an OS. So we can have containers that contain a host OS, those are just VMs, and then we can have containers that are instances that pass through into the OS and run in protected memory space. This allows us to have a great deal of elasticity and resilience for our hardware. VDI, or Virtual Desktop Infrastructure, is the process of running user desktops inside of a server-hosted VM. This allows us to have personalized desktops on any device that can access the server. So if I were to log in through a portal client or something similar with my laptop, I could access a particular desktop, which I could then access from my home computer through a VPN or my work desktop in any of the classrooms in which I work, which is pretty close to what happens with an Active Directory if you have mapped network drives as well. Virtual Distributed Ethernet, or VDE, this is a Ethernet compliant network that can connect physical computers and virtual machines together to allow them to pass information between each other. Because again, remember, virtual machines are supposed to be isolated so that way they behave in a much more secured fashion. Virtualization advantages. Well, there are many. New machines can be made available very easily if we need an extra one, so that means host availability is a lot quicker. Resources can be expanded or contracted as needed, which is called elasticity, as I mentioned a bit ago. We can reduce costs because we need fewer physical devices. This is kind of a double-edged sword because the devices that we do have probably have to be slightly more pricey. We can also provide uninterrupted server access in most circumstances. We can have live migration, which is where if a particular VM hardware component crashes, we should be able to move it to a different physical computer with no user impact. Maybe a little bit of shutter, but in general, that snapshot should be able to move from one to the other, especially if we have mirroring going on to be able to clone that data as it's being accessed. So some security advantages for virtualization. We can test out updates. Before we roll out to production lines, we can test it in a VM which is built with the exact same parameters. A snapshot of a particular state of a virtual machine can be saved for later use, so they're not time sensitive in the same way that a physical machine would be. And testing the existing configuration, also called security control testing, can be performed in a simulated network environment. Another thing that's handy is that suspicious programs can be loaded into an isolated VM and executed. This is where virus testing usually goes on. This is called sandboxing. If it's malware, only the only impact is on the VM itself, which means that we can then reset it to a pre-malware state and just act as if the malware was never present. Now, there are also some concerns. With every benefit, there is a cost, right? Not all hypervisors have the needed security controls to keep attackers out. Existing security tools were often designed for single physical servers, not for these multi-server virtual environments. VMs have to be protected both outside and from other local VMs because you can have what's called bleed or scrawl. VMs can escape from the environment and directly act with the host OS, so that means that we need to have some sort of escape protection built into our host OS. VM sprawl, as I just mentioned, is the widespread proliferation of VMs in an environment without proper oversight or management. Cloud computing. This is another one kind of attached to the whole virtualization thing. The on-premises model that most people used to do, which was where enterprises would purchase all the hardware and software needed to run their organization, meant that they had sunk cost in every piece of hardware they used, which was kind of problematic because if something failed, then you were immediately responsible for replacing it. You had to source it, have it shipped, wait, get it in, configure it. Hosted services are a little bit different. This is where we have servers, storage, and supporting infrastructure shared by multiple enterprises over a remote connection. So somebody builds this big, super powerful server farm, and then they can compartmentalize and host out portions of it to multiple companies. So that way, they're always getting the maximum return on their investment by having the maximum number of subscribers. And if one drops out, they can be elastic and be able to expand the services they offer to the model the subscribers that are still left. Cloud computing is a model for convenient on-demand access to a common pool of configurable computing resources. It's a pay-per-use model, so you only pay for what you need. In certain cases, it may be for however many gigs or terabytes of storage you need, how much clock time you need on a particular processor, if you're doing rendering, how much time you need on a graphics card or similar. The types of clouds that we will see will be public, private, community, and hybrid. So public, pretty well defined. It's available to all public enterprise. Private cloud is hosted privately but can be accessed by any member of that organization. Community cloud is where you have several organizations working from the same cloud services. And then a hybrid cloud is any combination of the previous three. From the service model standpoint, we have to look at these primary four models. Software as a service, which is where something like Photoshop, you log in and you can gain access to software running on cloud infrastructure. So this allows you to run things like Photoshop on very lightweight interfaces because you're actually accessing hardware that's running off-site. Platform as a service, this is where you install or run specialized applications on the vendor's OS and hardware. So rather than them providing everything, you are providing the software, they provide the OS and hardware. Infrastructure as a service is where you essentially are able to deploy and run your own operating system and applications just using the hardware availability. And then SecAAS is where community resources are pooled and cloud sourced to the consumer strictly for security services. So that can be for network analysis, monitoring, things like that. As you go up or down this chain here, you see that there is a greater or lesser extent to which the client is able to customize, but there is also much less obligation and responsibility. So of course, when there's less responsibility on the behalf of the consumer, they are paying someone to take on that responsibility. Remember our model, we can accept, avoid, diminish, or transfer a risk. If we're transferring a risk, we're probably paying for it. Cloud computing has some security challenges as well. Providers have to guarantee the means to be able to approve authorized users as well as denying imposters. Transmissions from the cloud have to be protected. Customer data must be isolated from that of other customers, and the highest level of application availability and security must be maintained. Often you'll have what's called a CASB, Cloud Access Security Broker. These are software tools and services, they exist as a set, that reside between the on-premises and cloud infrastructures. They act as a gatekeeper and ensure that enterprise security policies extend to cloud data. So again, it's just a third-party involvement to make sure that everything is behaving as it was expected. Last but not least, we'll talk about this this afternoon, software-defined network, or SDN. SDN virtualizes parts of the physical network to be more quickly and easily reconfigured, and it does this by separating the control plane from the data plane. So the physical controls become virtualized, and then the data plane is able to be segmented into whatever it needs. For traffic to then move across the network, we have to involve another piece of hardware called the SDN controller. The controller is then going to verify that the traffic that's being moved is permitted by enterprise network policy to move. Once this is approved, the controller will then compute a route for the flow of data and then add an entry for that flow to each of the switches on the route that has been designated. SDNs can help secure data by simplifying VLAN extension beyond the on-site perimeter. So again, we talked about a little bit ago how a CASB is going to help you make sure that enterprise policies are being enforced off-site. SDNs are able to do that as well, so that we can make sure that VLANs are able to extend to secondary and tertiary sites as well, so working with VPN or cloud instances. SDNs can also ensure that all network traffic is routed through a firewall, so kind of that whole single link formation for the aggregator / concentrator route. It also helps with data capture for NIDs and NIPs to make sure that information passes into the correct logging areas so we can identify potential intrusions, threats, or anomalous behavior. The graphic down here is a little bit of a redux from what we saw from the previous figure in the textbook, which I believe is 7.6. I wanted to draw it so it was a little bit clearer of what was going on. You see the data plane is separated from the control plane by the protocol list, and the control plane is separated from the applications by the API. If any of you are into modding of PC games, you'll actually know that right now, Nexus Mods, which is a really big mod site, is in the process of essentially archiving any mods that are left on the site after, I think, August 5th. And the idea is that in order to make sure that data is not disrupted for their new collections process, being able to set up custom load orders, they are now making sure that only through the API of the site, which can be accessed by internal users only, can be allowed to remove a mod from the site, as opposed to if you were to go in and just delete it from your profile. So now it's being moved away in terms of a measure of control. So this is kind of like the dark side of an SDN. When you start separating somebody's ability to control how that flow of information works, and instead of going from a direct access point, you start separating from layer to layer to layer, that can be problematic. So while SDNs are very helpful for being able to extend on-site boundaries to remote locations, it also means that there is a much bigger attack surface that's available because you start involving other computers and other infrastructure that you may not directly control. And that is Chapter 7. So if you guys have any concerns or comments, as per usual, you can always contact me via the YouTube page here. You can contact me through Blackboard, through my K4 email. You can contact me through my Google Voice number. So if you have any comments, ways I can do things better, I'm always happy to learn. I hope you guys are too. Thank you so much for your time and attention. I appreciate you more than I can say. And I hope you have a wonderful rest of your day, and I will see you next class.